Hello, students. Today we are going to discuss projectile motion. Projectile motion. A projectile is just an object that is freely falling. It could be going down to the ground straight, or it could be going up straight. It could be falling a trajectory like a basketball when you toss it into a hoop. It could be like a missile that has been fired, So as long as the only force acting on the object is gravitational force, then we are going to refer that as a projectile. Now here I have photographs of a moving ball. So these are the kind of photographs that we get if we take a multi-flash pictures. In other words, several pictures or pictures taken at equal time intervals, then we end up with this kind of photographs. I don't know, you might want to scrutinize or to explore, to pay attention to how the dots are spaced. Think about how the dots are spaced. Think about the vertical direction or downwards or sideways. How are they spaced? Is there an interesting pattern that you can observe? So think about this. Think about it. So you can pause the video, pay attention to the photographs and see what's going on. Okay. I know for now, you already see that the spacing are getting wider and wider as the object is getting down to the ground. You can actually see here that the spacing here is wider compared to the previous spacing here. So compare this and that. So that is one thing that you can explore. You can also explore what's going on with the horizontal or the horizontal direction of the projectile. What's going on? So explore that and try to think about what a projectile entails. Now here, I tried to break down the motion into the horizontal and vertical velocity components. So I broke down the motion. So if I try to map this dot upward, it goes there. Let me go there. This one goes there. I try to map this dot upward here, up, goes up. So if I try to do that, I can observe something all the way down there, all the way down there, all the way down there. So you can tell that what's happening here is that the horizontal component shows that the dots are equally spaced. They're equally spaced. If we do the same with the, let me see. If we do the same with the vertical component, like here, we have it here, we see that indeed what we predicted or what we observed first, the first image is the same. So you can see that. So right here, you can see that motion is actually accelerated. So you have, I'm sorry, this is accelerated motion here. And if you look at the horizontal component, this one looks like constant speed. Okay, so that's constant speed motion for you there. All right, so we learned something from the photographs. So we learned something. For example, acceleration. In the x direction, we see that the motion is uniform motion and the acceleration is actually 0. So the acceleration is 0. There's no acceleration there, 0 meters per second squared, because the motion is uniform. Remember, acceleration is the change in velocity over time. So the velocity is not changing, so acceleration is 0. For the y component, what I see is that there is acceleration. If I say downward is negative, then my acceleration can be written as minus. Well, I like to use usually 9.8 meters per second squared, but I'm going to use in this discussion 10 meters per second squared. The minus means acceleration is always downward. Whether an object is going up or is going down, the acceleration has to be negative. In other words, always points downward. I hope you remember Newton's second law of motion. It says that the direction of the net force is the direction of the acceleration. So here, acceleration is always going to be negative. In other words, downward. If we choose down as negative, up as positive. So in this case, acceleration is minus 10 meters per second squared. What about velocity? What about velocity? The velocity, if we see carefully there, velocity is constant. So velocity, if I want to look at velocity, I would say in the x direction, velocity x is always constant. So v equal to v x naught. In other words, velocity at any point in time is the same as velocity at the initial point. I'm going to use this notation as the following. To be v naught, but in the x direction. So it's initial velocity in the x direction. All right. And what about in the y direction? Velocity in general in the y direction will be given as vx, will be v naught x. In other words, initial velocity plus acceleration in the y direction times what? Times time. So this will be the equation that we'll be using to find the velocity. This is y here. All right. What about displacement? What about displacement in the x direction? Well, if the velocity is constant, then displacement x will just be equal to initial velocity, v initial velocity in the x direction, times what? Times time. So that will be the displacement. Because the velocity is constant, so just multiply velocity times time, you find how much you have displaced in the x direction. For the y direction, displacement will be what? Displacement y will be given by the usual formula. We are going to have v initial in the y direction times time, and then plus 1/2 acceleration in the y direction times time squared. So that will be our formula for the y in the displacement in the y direction. Okay, so in summary, we have seen that for any projectile motion, the horizontal component shows that the velocity is constant, whilst in the vertical direction, we have accelerated motion. In other words, the object is actually accelerating. So in order to solve most of our problems, we have to actually divide or think about the projectile's velocity as composed of horizontal and vertical velocity components. Let us look at examples. Example 1. With no air resistance, we can visualize how velocity components change. Assume that the initial velocity in the y direction is equal to 20 meters per second, and the initial velocity in the x direction is 15 meters per second. So draw velocity components of the ball at each point shown, assuming the dots are 1 second apart. All right, so what they're saying is that this is just 0 seconds, 1 second here. This is 2 seconds. This is 3 seconds, and this will be 4 seconds. Initial velocity, we are told that, let me use a red marker. We are told that this is 15 meters per second. Right, and then up is 20 meters per second, so about 20. So I'm about double that. I need to make sure I have enough space. So I'm going to put this as 15 per second. The other one is close to 20, so 20, maybe there. 20. Now that's at 0 seconds. That's initially 20. And now at after a second, I have to remember that the horizontal velocity has to be the same. So the same here. It has to be horizontal, but the same as before, 15. Don't think I have enough space. 15 meters per second. And now the vertical component, the velocity has to reduce. You know, the object is losing speed at a rate of 10 meters per second every second. So losing speed, I forgot to say that acceleration in the y direction here is minus 10 meters per second squared. So upward, I have to lose some speed. So about half of that. So that will be 10 meters per second because I'm going up, I'm losing speed. Around here, I only have horizontal component, still 15 meters per second, but there is no vertical component. There's nothing in the vertical direction because I have lost the other 10 meters per second after 1 second. All right, so moving from 0 to 1, I lost 10 meters per second. I go to 10 meters per second upward. And then another second, I lose the 10 meters per second. So I have no velocity in the vertical direction at this point. I only have the velocity in the horizontal direction. Now at 3 seconds, now I'm gaining speed downwards. So it will be the opposite of this point. So I'll go down like that. So at that point, I'll have 10 meters per second, but I'm going down. So I'll put a minus sign here. The velocity in the horizontal direction is always constant. So still 15 seconds, 15 meters per second here. And then finally, let me see if I can minimize this. Okay, yeah. Finally here, the horizontal component is still the same here. And then downwards, it has to be now the opposite of it was initially here. So add 20, so it'll be 20 meters per second, but downward minus there. So these are the velocity components. Okay, so now let's look at the question 2. Question 2 says, draw all the forces acting on the ball at each of the following positions below. Ignore air resistance. Well, first position, the force is always downward. Remember, as long as it's a projectile, it's in the air, where we ignore air resistance. So the only force is gravity. So FG here. Here, the only force is gravity still. Here, the only force is gravitational force. Here, it's the same gravitational force in this nearly constant. It's the same. So as you can see here, gravitational force points downward. Whether the object is going up or down, the gravitational force points downwards. There's a common misconception that there has to be a force in the direction of motion. There's a common misconception, but I want you to know that for a projectile, the only force has to be gravity, as I have drawn here. All right, question 3, draw acceleration vectors on the ball at each of the following positions below. Ignore air resistance. Complete the following table for a projectile. Okay, well, these are acceleration vectors. Okay, Vx, Vy, Vr. Okay. All right, we completed this already. We just have to go ahead and complete the table. Okay, so initially we were told that Vx is 15. So let's put 15 here. 15. Let me maximize it a little bit. 15, and then Vy was 20. I think this was, we were told at the beginning right here. We are told in this one. So Vx naught is this, and Vy naught is this. So I'm just putting those numbers. Acceleration times 0, there's no acceleration in the x direction, so I put 0. There's no acceleration because the velocity is constant. In the y direction, it's gonna always be minus 10. I can just complete this. I know it's always minus 10. minus 10. Don't have to worry about this. And this one also I can always complete it quickly because there's no acceleration in the x direction. Now, after 1 second, we already had this one that was, 15. This is 15. This cannot change because the velocity in the x direction is constant. This cannot change. But I have to be careful with this one. After 1 second, the velocity reduces to 10 because I am accelerating at this rate here. The velocity is reducing. I'm going upwards. So the velocity will be reducing by 10 meters per second every second. After another second, I lose all the speed. There's no velocity in the vertical component. Now, at 3 seconds, now the object starts going downwards. So the velocity in the y direction now will be minus 10, pointing down, then minus 20. All right, minus 20 here. So that's the velocity in the y direction. Okay, so that's how we complete the table. And as for drawing the acceleration vectors, we can just say that, acceleration is actually downwards all the time. So just like the forces were downward, so acceleration in the y direction is downward at each and every point. Okay, so acceleration is downward. Just like this diagram here. Remember, second law says that the direction of the net force is the same as the direction of the acceleration. So there'll be no change in terms of direction of the acceleration. Okay, let's look at the next question. This question. Complete the following table for a projectile above. The dots are 1 second apart. Assume initial velocity is 20 meters per second and initial velocity in the x direction is 15 meters per second and acceleration due to gravity is 10 meters per second squared. This is squared here. Okay, downwards. In other ways, they're telling us that AY is equal to minus 10 meters per second. It's hard to write at the corner here. Second squared. Okay. All right, so let's go on. Remember what we want this time around? V. Okay, this time around we want V. It's not Vx. Be careful here. It's not Vx or Vy, it's V. So V is actually the magnitude of the velocity of a projectile. So the first point, remember, in our initial diagram, we had this as 15 meters per second, and this one was 20 meters per second. The velocity at that point will be this one, will be the diagonal. If we try to complete the parallelogram, will be the diagonal, right? So that's the velocity. So we can actually use the Pythagoras theorem to find the velocity. Let me draw the situation here. So it's like having V, this direction, 15 meters per second squared, and up 20 meters per second. So what we are saying is find this. This is what we call V, the magnitude of that velocity. Just the magnitude. So we use Pythagoras theorem. So let's assume that this is V. Then we are going to say V squared is equal to, I'll just use the numbers without units, 15 squared plus 20 squared. And this is actually Pythagoras theorem. Pythagoras theorem. All right, then we can go ahead and find our V. All right, so go ahead, find V. So V here will be the square root of 15 squared plus 20 squared. So I'll use my calculator here. You can also try to do it wherever you are. Try to find the square root of that. So 15 squared plus this is 20 squared is got that. Then I take the square root I got 25. So for this one, I got 25. So 25 meters per second. All right, so I can go ahead and insert my answer here. Okay, so that will be 25. All right, so I can do the same now for the second position after 1 second. So let me see. I don't have enough space, so I'll have to erase all this. I'll do all the way to maybe 2. I mean, we'll see. I wish you could also try it and just finish this one. Okay. All right, so next, so we just have to remember that the next vector, this will be 15, and this will be 10. So now we are looking at V. I'll just go straight. In that case, V will be square root of 15 squared plus 10 squared. If you use your calculator, what do you get? 15 squared plus 10 squared, and then square root of that, according to my calculator, I got 18. About 18, I got 18, so I'll put 18 here. All right, the next one, just have to remove this. Okay. Our X component is 15. Oh, next one, no, sorry, here, 15. So I have 15 squared, but I don't have anything in the vertical direction. So 0 squared. If you do this, you get 15. So that'll be the speed, the magnitude of speed at that point, 15. Sorry. So that will be 15 here. All right. What do you think at point 3? What answer are we going to get? What do you think? You can tell by looking at the symmetry of the problem, but let's do it. All right, now at the next point, I know the velocity now here. We still have 15 here, but downward is going to be, remember, that will be 10, minus 10. Minus 10. So if we use Pythagoras theorem, what do you get? So the root x, Vx squared will be 15 squared plus minus 10 squared. What do we get? So let's try that. 15 squared plus 10 squared. Then raised to the power 0.5, or square root of that, I should say, is 18. Are you surprised? So we get 18, same as that. All right, can you guess what will be the last one? The last one, as you can guess, the speed will be 25. 25. All right, so that's how we find the velocity as the magnitudes, the velocities. Just make sure there is a difference between V and Vx or Vy. There's a difference. These are components, and this is a magnitude here. This is a magnitude here. The magnitude. All right, let's move on to question 5. Complete the following table for a projectile above. The dots are 1 second apart. Assume V naught y equal to 20, V naught x equal to 15. Now we want to find the displacements. So at time equal to 0, here where we start, there's no displacement in the x direction. Actually, this is our x line, the x's, and then up will be our y direction. So there's no y, there's no x. At this point here, our x will be this distance going this way. Our y will be this distance. So this is y, this is x. All right, now here I can use the formula that we talked about before. For example, x, if you remember, we said just multiply, since the velocity is constant, just multiply v naught x times time. Okay, so this will give us our v naught x is 15, and then you multiply by time, just 1 second. So that will be 15. So 15 here. All right, let's finish all the x's. Now I'll be changing the time because Vx naught is constant. When time is 2 seconds, sorry, so 15 here. And when time is, I change the time here to 2 seconds, then the distance in the x direction will be 30. Then I change the time to 3. If it's 3 times 15, 45. 45 here. Then I change the distance to what? To 4. 4 times 15. 4 times 15 will be 60. So 60 here. So that's how the distances change. Okay, the formula is just to multiply the initial velocity times time. Like that. Okay. Now, what about the y's? How do y's change? Well, why we have to be careful? Because for y we have to be careful. We have acceleration there, so we have to use the following equation. So y equal to initial velocity in the y direction times time plus 1/2 acceleration in the y direction times time squared. Okay, so let's start for 1 second. What will be the y direction? So I'm looking at this. What will be y after 1 second? Well, let's go here and plug in the numbers. Our initial velocity is 20. I want to use the units now. Okay, now time is just 1, and then plus 1/2. Remember, acceleration is downward, minus 10, and time is 1 squared. So that will give us the what? The y displacement. So this one gives me, if I do mathematics here, 20 minus what? Minus 5. So it looks like it's 15. So it looks like it's 15 meters. So let's go ahead and put 15 meters here. Okay, 15 meters. Now we have to change the time. The formula is the same. Now the time to 2. So I'm going to put this one. Okay, so I'll put this one 2 seconds, and here I'll put 2 seconds. What will be the displacement upward? So that gives me 40 minus you can put all this in the calculator and see what you get also. This is a 5 times 4. It's what? 20. So I got a 20 here. I don't know what you got there, but got a 20 as the displacement upward. So 20 meters. All right, so let's put the 20 over there. 20 meters. Okay, and then let's change our time to 3. Time to 3 and see what we get. Time to 3. This will change also here. So if I do that, what do I end up with? Well, that one. So it'll be Okay. Okay, so it's 20 times 3, 60. And then minus 5 times 9, 45. That's 15. Okay, so let's see. Mm. 16. Okay, so we have 5 times 3 squared is 9. Oh, so I got 15. Oh, okay. 15. Oh, times 3, 3 seconds. So let's see that point. Yeah. This was 0 seconds, 1 second. This is a 2 seconds. That was 20. Now I got 3 seconds. So here we got what? We get 15. So we are going down again. So the y will be 15. 15 here. All right, and then the last one. Let me see. Sorry. You can tell already what will be the last one, but let's try to change. Oh, this one was 15, but now the last one, I'm going to change 3 to 4. 4. Change this to 4. And then we'll find out what will be the answer for that. So that will be 8 minus 16 times 5. So that will be minus 5 times 16. Okay. So that one, let's see. That one will be 0 because this part end up being 8. This part be minus kind of like 5 times 4 squared is 16. So that should be 8, so 0. So back to 0. So we start in the y direction. We start from 0, 50, 20 is the highest we can get. Then you go down to 15, then 0. All right. Okay, now let's look at this question here. The same range is obtained from 2 different launching angles when launching speeds are the same. So launching speeds are the same and their angles add up to 90 degrees. So when the launching speed is the same and the angles of projection, like here there's a 30 degrees angle of projection here, 34. If we add up the launching angles and we find that it's 90 degrees and the initial speeds are the same, then we know that we are going to have the same range. So this is the range. The range is the distance from where the ball is projected to where it lands. That's the range. It's called the range of a projectile. It's defined this way. So what is the missing launching angle? In other words, what's the launching angle of this projectile? Well, according to what we have learned from here, they are telling us that if we add up the 2 angles, they must add up to 90. So 34 degrees plus x, we don't know that. The answer must be 90 degrees. Sorry, 90 degrees. So here x will be 90 minus 34. So you can try that. 90 minus 34, you got 56 degrees. So The other launching angle is 56 degrees. Which ball touches the ground first? One that is dropped from rest, or the one that is fired horizontally? That is fired horizontally. Well, by the way, I got these images. You can actually practice this using the fade simulation. These ones are fade simulation. So you can Google the fade simulation, and then you'll be able to actually try this experiment and see which ball touches the ground first. One is just dropped, and the other one is fired horizontally with a certain speed. You fired horizontally with a certain speed. Which one touches the ground first? If you go to the fade simulation and then look at projectile motion simulation, projectile motion, and try this experiment, it'll be interesting. Try this experiment out. I also invite you to try this experiment out. So go to fade simulation, projectile motion. Try out this experiment. So try out this. Okay. So if you try out this, you realize that they touch the ground at the same time. Okay. So same time. So the reason has to do with the way we understand that the initial velocity for both is actually 0. Okay. So the initial velocity, what we call V initial in the y direction, is 0 meters per second for both projectiles. All right. So for example, the one that is dropped, obviously the initial velocity in the y direction is 0. It starts from rest, right? Starts from rest. And the one that is projected horizontally, although it has initial velocity, but it is only in the x direction. There is no velocity in the y direction because the angle of projection is 0. In other words, it's horizontal. Okay, I hope that makes sense. No initial velocity in the horizontal direction. So if you think about that, acceleration is also 0. Acceleration in the y direction is the same, minus 10 meters per second, and the same for both. They touch the ground at the same time. So they touch the ground at the same time. All right, if you want to use some mathematics, you can remember that y is equal to velocity initial in the y direction times time plus 1/2 acceleration in the y direction times t squared. Since initial velocity is 0, this goes to 0 here, you end up with this equation, and you can see that y equal to 1/2 a y t squared. So from this equation, since actually we have to respect the fact also that y is the same, height is the same. When we make these conclusions, we have also to remember that y is the same for both. Y is the same. You drop them from the same height. So y is the same. Y is the same. Acceleration is the same, and therefore they'll have the same time. Right. If you try to calculate the time here, having dropped from the same height, y is the same, and ay is the same for both, and this vy is the same. Therefore, t is same. Okay, you can reason like that as well. Try out this using the simulation from the fade simulation on Google, University of Colorado. All right, that's the last question here. A marble sits near the edge of a 125 meters high platform It is then ejected horizontally with an initial speed of 8 meters per second. Acceleration due to gravity is that, ignore air resistance, determine the time of flight. Determine the time of flight. All right, so time of flight. If you look at the equations I showed you, the time of flight can be found from one of the equations. I remember I shared a table with equations. This equation will help us to find time of flight. This one. When you want to find time of flight, that one usually helps. But the key, the way I do it, you try to find, or you try to write down what's known and what's given. So in general, what do they say? Given. So what are you given? So you list what you're given. So if they say a marble sits near the edge of a 125 height platform, that means I'm given Y there. Okay, so it means that this Y is given. So the Y position is given as, since this might be like a zero line, in other words, Y equal to 0. Therefore, Y here is downward. So that might be 120 minus 125. Minus 125. See, so we're given Y as minus 125 meters. And what else are we given? We are also given acceleration, which we already know, minus 10 meters per second squared. And what else? We are given V initial in the Y direction. What is that? Well, that is 0, because the only thing we are given is velocity in the X direction. So that is actually 0. That's given, actually. Should be able to tell from the program. There's no velocity in the Y direction initially. There's no velocity. So we are given all those variables in the Y direction. And of course, we are also given V naught X as 6 meters per second. Okay, it's always important to say, what am I given? Then you say required to find. So you are required to find time of flight. So that will be T. Okay, then you say equation. If you go to the list of equations, you realize that given all these variables, these ones are the variables given, you require this equation, Y equal to V naught Y T plus 1/2 AYT squared. All right, that's the equation that will help you to find the time of flight. That's what has the time in it and has all the required values. This part goes to 0 because there's no initial velocity in the Y direction. So basically you are ending up with Y equal to 1/2 AY times T squared. Then from here, we can find our time by multiplying both sides by 2. So 2Y will be equal to AY times T squared. So I multiply both sides by 2 of this equation to remove the fraction, 1/2. So multiply by 2 both sides, you end up with 2Y. If you multiply by 2 this part, the 2 drops, you end up with AYT squared. Then you can divide this equation by AY, divide this by AY, cancel, you end up with the time squared equal to 2Y over AY. And then to find the time, you take the square root of both sides, take the square root of this side, take the square root of this side. This will give you time equal to square root of 2Y over acceleration in the Y direction. So that is the formula for time. Then you can go ahead and say time is equal to root 2 times minus 10. Remember, we're using minus 10. I'm sorry, this is Y, so minus 125. Remember, the Y is minus 125. And you can go ahead and check also here. We said Y is minus 125. And see, where are we? Okay, divide by acceleration in the Y direction is minus 10. Okay, If I do that, I do this, I put it in my equation, what will I get? I'll get 2 times 1 minus 1.5. By the way, these negatives cancel out, so because they appear in the numerator and denominator. It looks like I'll get square root of 25, which is 5 seconds. So 5 seconds there. So that's the time of flight of the projectile. Okay, the other one is determine the horizontal distance from the edge to where the marble lands. So we want to find the horizontal distance. It's like all the way there. So we are looking at, yeah. Okay. Okay, so that's the horizontal distance. So let me remove this. Okay. So this is the horizontal distance I'm looking for. And if you look at the formulas we have seen so far, this tells us what? X will be initial velocity, which is always constant, then times the time. And we already know the initial velocity is 6 meters per second. And the time is what? What is the time of flight? 5. We just calculated this one as 5 seconds. Okay, so if you do this, you get 6 times 5. That will be 30 meters. The seconds will cancel out. So 30 meters, that will be the displacement you're looking for. Okay, and now we have to, you might want to, let me minimize it, take a picture of this. I want to erase this. I want to solve the last problem. So take a picture, and I'm going to erase it now. The last question, they say, determine the magnitude of striking velocity. We want to find the striking velocity. In other words, what is the magnitude of the velocity? Just the magnitude. We don't want to talk about the angle. Just the magnitude, just before the marble strikes the ground. That will be our last problem. That will be our last problem in this discussion. Okay, so what you are saying here, it's freezed. Okay. If the marble is fired there, it will go like that all the way down. And the striking velocity will be the velocity like this. Now, this striking velocity is V. It is composed of 2 velocities, one velocity in the horizontal direction and another velocity in the vertical direction. We call this one Vx and we call this one Vy. And if I know Vx and Vy, I can use Pythagoras theorem to find V, because V squared will be Vx squared plus Vy squared. Now remember, I can also write this as this. This can be written as this one, and then write this one here. So this could be Vx, this would be Vy, and this one can be here. So I can also write this as that. This will be our V. Okay, so this forms like a Pythagoras theorem. So Vx squared plus Vy squared will be equal to V squared. Okay, I can also write it like that. So my goal is to know what is Vx and what is Vy. So if I ask you, what is Vx? Well, remember, we initially fired the ball at 6 meters per second. So if it's a projectile, then Vx doesn't have to change. It's 0.6 meters per second. So we know for sure Vx doesn't change. It's the same as initial velocity. So it's the same as the initial velocity in the x direction, 6 meters per second. So this one doesn't change. That's good. What about Vy? Well, Vy, I can find Vy by using this formula. Vy is equal to V naught y plus A remember, AYT. I don't know if I shared that equation before, but this is how we find Vy when the acceleration is constant. Let me go, if I share that equation in the table. Yeah, okay. I forgot so this has to be Vy. These ones were supposed to be Vy, so I'm sorry here. So these ones are supposed to be Vy, and this is Vy. Okay. So this is the equation actually here. I had to put Vx, but it's Vy's. Okay, that's the equation. Find the velocity. So sorry about that. I hope I'll fix it when I post the video. Okay. All right, so that's how we find Vy. And then Vy naught is actually 0. So Ay is minus 10. The time of flight was 5. So the Vy will be minus 50. Minus 50 meters per second. All right, so then you can go ahead and find your V. So V will be square root of Vx. Vx is what? 6 squared plus minus 50 squared. That will give you the magnitude of striking velocity. So it's plus. All right, I'm trying to do it here. You can also do it. Let's see what you get. All right, I got 50.3, 50.4. So 50.4 meters per second. So that will be the striking velocity. Let me try it again. Squared plus squared. Yep, 50.4 meters per second square. Yeah, per second, sorry. All right, so that's the end of the practice problems or discussions. Let me know if you have any question. Bye for now.